Today we will prove the second Sylow theorem. Here's the statement of Sylow theorem number 2. It says in words that any two p Sylow subgroups of a group G are conjugates of each other. Okay, more precisely, if p divides the cardinality of a finite group G, in other words, we write the cardinality of G as p power d times m. So d is some number 1 or more, and m can be again similarly 1 or more. And suppose we have two subgroups H and K of G whose cardinalities are equal to p power d, the maximum power of p which divides the cardinality. In other words, H and K are what we call p Sylow subgroups. Then we can find a group element G such that H can be written as GK G inverse. In other words, H and K are conjugates of each other. Okay. Now let's prove this theorem, and for the proof we will recall something that we talked about in one of the earlier videos on group actions. So recall we have an action of a group G on itself. This is the translation action, but recall there are actually two such actions. Okay, so this is, remember, there is something called left translation, which is the following action: the group element G acting on, well, the element X. So I think of X again as being an element of the group G, but now it's the set on which the action is taking place. This is defined as G multiplied by X, right? So this is called the action by left translation, and there is similarly an action by what's called right translation. And if you recall, this involves a little twist. So G acts on G as follows: G, this is the right translation action, so maybe I'll put a different symbol for now. G acting on X by right translation is you have to multiply G inverse on the right. Okay, and remember that it's important to put the inverse, otherwise this doesn't satisfy the compatibility axiom for an action. Okay, so there are actually two translation actions, the left translation and the right translation action of a group G on itself. And in fact, it's probably sometimes more powerful or more advantageous to put them both together. Okay, so in fact, what the left and right translation actions do is the following interesting thing: they actually define an action of the cross product G cross G. So remember the definition of cross products of groups, the direct products. If I have two elements, so what is this new group? The elements are of course pairs G1 comma G2, and the multiplication operation is just component wise. So I take G1 G2 multiplied by H1 H2 is just G1 H1 comma G2 H2, right? So this is the definition of the cross product, and we actually can define an action of the cross product G cross G on G, and this is maybe what should most appropriately be called the two-sided translation action. So what is this double-sided or two-sided translation? The action is the following. Okay, so this is just recalling what the multiplication operation on the cross product is. So here's the definition of the action. So how do I make G cross G act on G? So I take a pair G1 comma G2, this is in G cross G, and I take a point X in the set. Well, here the set is G itself. So let me define the action. The pair G1 G2 acting on the element X gives me, well, I use the first G1 to do a left translation and the G2 to perform a right translation. Okay, so the action definition is this G1 G2, the pair acting on X, gives me G1 X G2 inverse. Okay, so this is a two-sided translation, and here's a little exercise which I urge you to do, which is to check that this is an action. Check that this is an action. This defines an action. Okay, so this involves first looking at what the definition of the product on the cross product is and so on. So this is a nice little exercise which puts together all the things you have learned until now: cross products, definitions of actions, and so on. Okay, So in fact, what we have is not just right and left translation, but really you should stitch them together and think of it as giving you an action of the group G cross G on G by means of this two-sided action. Okay, so that's maybe the most general way of thinking about translations. Now, why is this relevant to our proof of the second Sylow theorem? Well, that comes from the following. Okay, so when I have an action of a group, in this case the group G cross G, when I have an action on a set, so when G cross G acts on a set, in this case the set is just the group itself, then recall whenever I have a group action, it automatically defines an action on subsets. Okay, so I can make the group G act in fact on the power set of the set X. So here the set X on which the action takes place is G itself. So this is the action on subsets that we define. Okay, and in fact we refined this a little bit. We said we don't need to look at the entire power set. In fact, it defines an action on subsets of any given cardinality. Okay, so I can look at pkg for any cardinality G. Okay, but recall that the value of k that was somehow relevant to our situation is, so let me just not confuse notation here, let me just keep G. So recall that the cardinality that was most relevant to our situation was somehow this number p power d. Okay, so in other words, because there is this two-sided action on the group G on the set G, there is also a two-sided action of G cross G on the set of all subsets of cardinality p power d. So recall this is just the subsets of G whose cardinality is exactly p power d. So there is an action on all such subsets, and just to recall, what is that action? If I give you a pair G1 G2, so this is the action. If I give you a pair G1 G2 in G cross G, its action on the subset A is just given by, well, it just gives me a new subset whose elements look like this. It takes every element of A and it applies the two-sided action to it. Okay, so I get G1 small a G2 inverse for every element small a in capital A. Okay, and take the collection of all such elements, that will be another subset whose cardinality is p power d. That subset is what you define the action to give you that subset. Okay, so that's the definition of the, I'm just recalling the action on subsets definition. Okay, now let's go back to, let's just look at the hypothesis of Sylow theorem 2 again. What is it that we need to prove? We need to show the following: if I have two Sylow subgroups H and K, then I can somehow relate them by a conjugation. One is obtained from the other by a conjugation. So I'll use the same notation. I have two subsets H and K. So observe, so what is it that we just said? I have G cross G acting on the set of all subsets of cardinality D of G. Okay, and let me call this as my set X now. Okay, now since G cross G acts on X, so recall the very important fact about X that we proved, which is that the cardinality of X is not divisible by P. Okay, P cannot divide the cardinality of X. This is the very interesting thing we proved, and recall the way we proved this was by observing that the cardinality of X is in fact nothing but the binomial coefficient p to the d m choose p to the d, and again by our group actions principle we managed to show that, or our fixed point principle, we managed to show that this number is congruent to m modulo p, and since m is not divisible by p, cardinality of X is also not divisible by p. Okay, so this was how we showed that X has cardinality which is not divisible by p. Okay, so now we have the following interesting thing. We have a group acting on a set whose cardinality is not divisible by p, and inside this group let's consider the following subgroup. So remember, I had H and K as part of my, so this is what I need to prove. I'm now going to prove the second Sylow theorem. So recall that H and K were both subgroups of G. That implies that the cross product H cross K is actually a subgroup of the group G cross G. Okay, so verify again. Here is another little exercise. Check that H cross K, which is by definition the set of all ordered pairs H comma K when H comes from H and K comes from K, check that this is actually a subgroup of the group G cross G, is a subgroup of the group G cross G. Okay. Now, having done this, so I mean assuming you have done this exercise, what is it that you get? Now observe, what is the cardinality of this group H cross K? Well, by definition it's all ordered pairs, so it's cardinality of H times cardinality of K, and so each is a power of the prime, each is in fact p to the d, so the net cardinality is p to the 2d. Okay. So what does that mean? It means that H cross K is in fact a p group. So in other words, H cross K is a p group, its cardinality is a power of a prime. Okay, now we are slowly bringing things into the formalism of our fixed point principle. Here is a p group, okay, and here is a set X whose cardinality is not divisible by p. Okay, so I have the two ingredients that I want. I have a p group, I have a set X, and in fact there is an action of this p group on this set X. Why is there an action? Well, observe that the entire big group G cross G acts on X. Okay, and this is after all a subgroup of the big group. Okay, so when you have an action of the ambient group, the bigger group acting on a set, you automatically get an action of any subgroup by just restricting the action. In other words, you just say, if I take an element from the subgroup, it acts the same way as it would act as an element thought of as an element of the big group. Okay, so this is just by restricting the action. So you can make H cross K act on X by restricting the action of G cross G on X. Okay, so we have all the right ingredients. So by our fixed point principle from one of the earlier videos, by our fixed point principle, what we obtain is the following, that H cross K action on X must have a fixed point. There must be, so what's the correct notation? X was the set, H cross K is the group acting on it, so this is the set of fixed points. This set is non-empty. Okay, the set of H cross K fixed points in X is non-empty. Okay, now what does that imply? So let's just unravel the definition. So this basically is now, well, let me just skip ahead. This is going to tell us that Sylow Theorem II holds. Okay, so Sylow Theorem II is essentially just this fact, that's all. It's the same, if you wish, it's equivalent to saying this statement here. Okay, so why does the H cross K fixed points, why does that imply Sylow Theorem II, right? So this is what I need to prove. So let's unravel this definition a little bit. So X H cross K is not empty means there exists a fixed point. In other words, there is a subset. So there is an element A in X such that A is fixed by every element of H cross K. So such that H cross K acting on A gives me A for every pair H comma K in H cross K. Okay, now what does this mean? A is an element of X means that A is a subset of the group whose cardinality is p power d. So those are the elements of X. Okay, so A is a subset of cardinality p power d such that the action of Hk on A gives me A. Now remember, what's the action of Hk? It's left multiplication by H, right multiplication by K inverse. This gives me A for all elements, for all pairs Hk in H cross K. Okay, so this is what's meant. So if I multiply, so if you recall, H A K inverse just means I take all elements of the form H small a K inverse and A runs over capital A. Okay, so that is equal to capital A. So now let's look at this statement here. Now let's do the following. Let's put, for example, so let me pick any element of A. Okay, so let me skip to the next page. So let me just rewrite that equation again. H A K inverse gives me back A for all pairs H comma K in H cross K. Okay, now let's do the following. Let's put K to be the identity element. Okay, what this means is that if I take H A, it gives me A because right multiplication by K inverse does nothing. Okay, So what this means is that H multiplied by A will give me A for all elements H in H. Okay, so in particular what this means, let's fix an element A. So let's pick any element, fix an element A in A. Okay, so what do I conclude? This means that HA belongs to A for all H in H. Okay, so that's really the statement here. If I take this element A, which comes from capital A, and I multiply it on the left by H, the answer is again an A. Okay, but what does that mean? Well, what is this now look at this elements of the form HA as H runs over H. So this is exactly the right coset HA. Okay, so observe the right coset HA is nothing but that's exactly the set of elements of this form, H coming from H. Okay, so saying that every such product HA belongs to A just means that this entire right coset is in A. Okay, but observe the following: the right coset HA has the same cardinality as H, right? So right cosets have the same cardinality as the subgroup themselves, and that's the cardinality is p power d, and in fact that's also the cardinality of A. Okay, so what that means is that this right coset here HA and this set A here both have the same cardinality. Both their cardinalities are p power d. Okay, and one is a subset of the other, which can only happen if they are actually equal to each other. Okay, so this means that HA must actually equal the set A. Okay, now similarly, so we can do the thing on the other side as well. We can put H to be 1 and conclude by a similar token that if I take this element A and you multiply it on the right by elements of K, then this is a subset. AK is a subset of A for the same reason. And again, because the cardinality of AK is the same as the cardinality of K, which is p power d, this again means that the right coset AK and A have the same cardinality. This means that AK is equal to the set A. Okay, so we have made the two conclusions that we are looking for. One is that HA is A, the other is that AK is A. Okay, so this right coset, a certain right coset of H is equal to sort of the corresponding left coset of K. HA is the same as AK, both are equal to the set A. Okay, now we are done, because observe, what does this say? The right coset HA is the same as, well, both are equal to A, but what does this mean? This just says that H is AKA inverse. Yeah, in other words, H is a conjugate of G. Conjugate of K. Okay, so this proves Sylow II. Okay, so again, as you see, the Sylow theorems are all instances of just one basic principle, that a P group acting on a set whose cardinality is not divisible by P will have to act by fixed points, and this property characterizes P groups in the sense that the converse is also true, right? So the converse is what was used in Sylow I, and sort of the forward principle is what's used in the proof of Sylow II. Okay, next time we'll prove Sylow theorem number 3, which is again an application of the same principle.